Welcome back to The Explainer. Today, we're going to connect some pretty big dots. We'll start with the physics problem that literally stopped the computer industry dead in its tracks. Then, we'll see the hardware revolution it sparked. And finally, we'll get to the big new challenge it created. How in the world do we actually command the powerful AI that was born from all this?
All right, so let's dive right in with this quote, because it really sets the stage perfectly. See, for decades, we all got what you could call free performance. Your software just ran faster on next year's computer. Simple. But as this quote points out, that super predictable, easy path, it just hit a wall hard. And the roadblock, it wasn't a lack of smart ideas. It was the laws of physics.
So let's start by digging into that original problem. We really need to get our heads around the physical limits that forced the entire industry to just completely rethink how you even build a faster computer.
And the issue, well, it was actually pretty simple, but totally profound. The faster you made a processor's clock speed, the more heat and power it sucked up. We're talking unsustainable levels. Push it any faster, and you were literally risking a meltdown. So that old, beautiful promise that your stuff would just get faster next year, no questions asked? Yeah, that was officially broken.
Okay, so what happened next is the really crucial part. It was like a fork in the road for computer hardware. On one path, you had CPUs. They tried to keep the old world alive, right? They got super complex, using all these clever tricks like prediction and massive caches just to keep those old-school single-file programs running fast. But GPUs, they took the other path. They basically said, nope, parallelism is the future. Instead of trying to hide how slow memory is, they just decided to outrun the problem by doing thousands of things all at once.
All right, so that brings us to the solution that came out of this big shift. And man, it didn't just tweak things, it completely redefined what high-performance computing even is. This wasn't some minor update, it was basically the birth of a whole new kind of computer.
So these new machines, GPUs, they are absolute masters of something called data parallelism. And here's the key insight, the real magic trick. GPUs don't create the parallelism. They just exploit the independence that's already sitting there in the data. Think about it. When you're processing a photo, the color of one pixel doesn't really depend on the pixel next to it, right? So a GPU can just say, great, I'll work on all of them at the same time.
For a while there, using GPUs for anything but graphics was super awkward. You literally had to trick the computer into thinking your science problem was, well, a graphics problem. But then came NVIDIA's CUDA. And that was the turning point. It was this big, loud acknowledgement of what GPUs had really become. These incredibly powerful, general-purpose parallel computers. And that, right there, is what unlocked their potential for science and, of course, for the AI revolution we're living in now.
Okay, but here's the twist in the story. Now that we have all this unbelievable parallel power, the bottleneck, it's moved. It's not about raw number crunching anymore. The new challenge, the big question on everyone's mind, is about communication and control. How do we effectively, efficiently, and maybe most importantly, safely command these new AI systems?
And that brings us right to the heart of what we're talking about today. We are seeing the rise of a totally new layer of software, something we're calling an AI command layer. Think of it as a set of protocols and systems built to do just one job. Translate what we, as humans, want into specific verifiable actions that an AI can carry out, both reliably and safely.
Okay, to make this less abstract, let's look at two real-world examples from NVIDIA that show this command layer in action. And they're at two totally different scales. First, we'll see how you teach a single specialized AI agent a new trick, and then we'll zoom way out to see how you orchestrate a massive, complex system like an entire warehouse.
All right, so put yourself in this situation. You've got a brand new, super specialized command line tool, and you want an AI agent to learn how to use it. But here's the catch. There are 0 examples of it online for the AI to learn from. None. And you absolutely positively cannot risk it getting a single command wrong. So, what do? How do you teach it?
Well, the solution is this really elegant 3-step recipe. First, since you don't have any real data, you just make some. You generate high-quality synthetic data. Step 2, you use this technique, and it sounds fancy, but stick with me, called reinforcement learning with verifiable rewards. All that really means is you build a system that automatically gives the AI a gold star for getting commands perfectly right and a penalty for any mistake. And then, the crucial third step, you build in that final safety gate. You always ask a human for the final OK.
And this is what it looks like in practice. It's just a safe, totally controlled conversation.
The human asks for something in plain English. The AI proposes a perfectly formed, totally valid command. And then, and this is key, it just waits for approval. That right there, that's a command layer in its purest form. You've got intent, translation, verification, and then only then execution.
Okay, now let's zoom way, way out. We're going from a single little agent to an entire intelligent warehouse. And here, the problem isn't just teaching one new tool. It's about orchestrating dozens of totally separate systems. You've got planning systems over here, management systems over there, IoT sensors everywhere. They're all spitting out data, but none of them are talking to each other. And the result? Just massive, massive inefficiency.
So NVIDIA's solution is to basically promote the warehouse AI to be the central command layer. It acts like a unified brain for the whole operation. It plugs into all those different data sources, takes that messy, fragmented data, and turns it into something you can actually use. Actionable intelligence. And then it coordinates all these little specialized AI agents to optimize everything, from when a forklift needs maintenance to scheduling workers and making sure safety rules are followed. It completely flips the script, moving the whole operation from just reacting to problems to actually getting ahead of them.
Okay, so we've seen how to command an AI safely, and we've seen how to orchestrate a whole army of them. But there's another huge piece of the puzzle: cost. Every single time we talk to an AI, our words get broken down into little pieces called tokens, and every single one of those tokens costs money. It might be a tiny fraction of a cent, but it adds up like crazy. So making this communication efficient isn't just a nice to have, it's absolutely essential to making any of this affordable.
And this is where a really fascinating system comes into play. It's a patent-pending protocol called the Universal Command Protocol, or UCP for short. Its entire reason for being is token optimization. The whole idea is to create a kind of standardized, super compressed shorthand for AI commands. Think of it like a secret, efficient language that makes talking to these big AI models way, way cheaper and faster.
And the potential impact. I mean, it's just staggering. By taking those long, wordy, expensive prompts we write and squishing them down into this compact, standard format, the USCP folks are talking about a potential 600 times cost reduction. 600! That's not just an improvement, that's a complete game changer for the entire economics of AI. So let's look at how this actually works. This diagram from the patent docs shows the basic flow. Over on the left, your device sends a request to an encoder service. That service looks up the request in a protocol dictionary, it's like a translation book, and turns it into one of those super compact UCP commands. Then that little command gets sent over to the executor service, which uses it to talk to other services you might need, like Stripe or Twilio over on the right. But one of its absolute cleverest tricks is caching. It's pretty simple, really. As this flowchart shows, when a new command comes in, the first thing the system does is check its memory, the cache, to see, hey, have I seen this exact command before? If the answer is yes, it can just spit out the old result. It never even has to bother waking up the expensive AI model. Super smart.
And this right here, this is where it gets really futuristic. Because that UCP command is so tiny and compact, you can actually encode the whole thing into a QR code. This allows for what they call a zero-token transfer. You could have one device securely issue a command to another one with no internet and no expensive call to an AI model at all. Just scan and go. How cool is that?
All right, let's pull back and tie all these threads together. Because when you look at all these different approaches, a really interesting bigger picture starts to emerge.
You know, when you put these case studies next to each other, a super clear pattern just jumps out. The NVIDIA agent, the warehouse AI, the UCP protocol, they're all solving different pieces of the exact same puzzle. How do we build a solid, reliable, and efficient command layer for AI? It doesn't matter if the problem is safety, or connecting systems, or just saving money. The answer, again and again, seems to be creating a structured protocol, a clear set of rules for communication.
So here's the final thought I want to leave you with. The next great frontier in AI, it might not be about building bigger and bigger models. It might be about designing the very protocols, the languages, they use to interact with our world. As AI becomes the middleman for more and more of our lives, these command systems stop being just code. They become the new rules of engagement. And that leaves us with a huge question. Who gets to write the protocols that are going to run our world?